Hello, everybody.
Hello, Jay.
All right. As a bad Simpsons reference, if I can get 2 or 3 people to laugh up front, lighten the mood for the rest of the talk, because the rest is going to be somewhat serious. Anyways, so what we're going to cover today, we're going to start with a quick overview of Redis for those of you who've not seen it before or used it before. And we're going to move on to a particular problem that I like to call monthly unique return and churn. And we'll go through 3 different methods of solving this problem. The first one, what I call the too much memory method. Then we'll move on to the reasonable memory method. And we'll finally get to the very low memory method. I know these are very difficult to remember, but we'll cover them again. And then we'll move on to visitor action sequence analytics. We'll have 2 different methods there. One is the sequence method, and the other is the low memory method. As you can see, there's kind of a trend here. We try to use less and less memory as we move on. And finally, we're going to get to geographic notifications with partitioning. And that's where the asterisk comes in. This is not analytics. This is just, hey, a fun application. And all of these 3 problems more or less stem from the same place, which is the Redis mailing list. Many of the problems that are in my book come from the mailing list. These are people who've asked questions that are interesting, unique, and that for one reason or another I decided to reply to and solve. And these are some of the other questions, and the reason I'm covering these now is because they've been asked since I finished writing the book. Speaking of which, the book will be in dead tree form in the next couple weeks. I signed off on the manuscript last night and signed off on the index earlier today, so soon, I promise. Don't hold me to that promise. It's out of my hands at this point. All right, so first problem, or the first part is the quick Redis overview. Generally speaking, Redis is a remote key to data structure server. That is, every structure that you have, or every bit of data that you have, starts out with a key. Very much like a key value store, memcache, and a variety of other things. But where Redis differs is that you can store different types of data. If you want to hold off, if you don't want to take pictures, I'll be uploading the slides later, so it will happen. The first structure is strings, integers, bitmaps, and technically speaking, floats as well. Yes, floats are relatively new in Redis 2.6, and I haven't updated my brain quite yet. And so these are kind of sort of scalars and individual values. And then Redis also supports lists of strings. So if you decide you don't just want one string, you want a sequence of them, you have them. Redis also supports sets of unique strings. Okay? And these are very much like lists, except they are unordered. They're backed by a hash table typically. There's some optimizations for strictly integer numbers. Those are optimizations. Then Redis also supports hashes that map to a string key to either a string or integer or floating point value. Now, this final structure, sorted sets, are a little bit unique to Redis, and I've not seen them in other places before. It's kind of sort of like a hash. You map from a string member to a floating point value, or score. And the unique thing about it is you can access items based on member. Members are all unique. But you can also, in addition to accessing by member, you can also access by sorted order based on score. Which is to say, if you want to pull things out, if you want to scan ranges based on score of 25 to 35, you can. Or if you want to scan from index 0 to index 100, or index -10 to -1, which would be the last 10 entries, you can. This is basically how you build sorted indexes if you want to do that kind of thing. And so these are the basic data structures that are available. Redis supports replication. So You can have multiple slaves. You can even set up slave trees, so you don't necessarily have to have, your master doesn't need to fan out to all of your slaves. You can have a master that fans out to some slaves, which then fan out to other sets of slaves, and that just works. Redis also supports publish subscribe, so you can subscribe to a key or even a key pattern, and anyone that subscribes will receive a message when somebody publishes to that key or a key that matches the pattern that you subscribe to. Redis also supports Lua, server-side Lua scripting. You can think of it like stored procedures in a standard relational database, only they're a little bit less flexible just because of the way Redis works. I'm not going to go into that because I could probably spend about 20 minutes talking about that alone. And then Redis also supports client-side sharding, and server-side sharding is in progress. Okay, that server-side sharding project is what is called Redis cluster, which also will support automatic resharding. It will support automatic levels, number of replicas, things like that. That's not done yet. Will be done at some point in the future, just not quite yet. Continuing on, the first problem that we're going to look at is, again, monthly unique returning churn. And we can more or less loosely define the problem as to say you've got millions of monthly visitors, okay? And also say that you need to know the monthly churn, how many people are returning from last month, how many people are new visitors, and how many people are returning, and how many people are maybe from several months ago. And one of the big problems is we don't want to waste too much memory, because arguably keeping these statistics is kind of sort of waste. You can use that memory for any one of a dozen other purposes, including caching your website, doing more interesting analytics on your data. And so we just want to try to minimize this as much as possible. And so now we come to my first solution, which I call the too much memory solution. And this particular solution is a little bit embarrassing. I say it's a little bit embarrassing because I came up with this solution and it's crap. In fact, this is the first idea that came to my mind after seeing the problem and having it hang around on the mailing list for about a month and a half. And I was the first person to reply with this particular answer. And once I realized how crappy it was bad. And I only realized when I was starting to think about what this talk was going to be on. So, step one is to generate unique identifiers for every user, and we're going to store it in a browser cookie. Okay, because all of our visitors are coming from a browser of some kind or another. Our second step is actually to use a hash to map from UUIDs to small integer IDs. And the reason for this will become clear in a moment. But then because we want to be able to clear out this small IDs, which I'll explain why in a second, we want to map, we have to create a secondary hash that maps from the small IDs to the UUIDs. Okay, so now we get a little bit of data duplication. And it doesn't get any better when we create a Z set of short IDs to timestamps. Okay? So that we can clean it out, because if you have old short IDs, you want to be able to clean them out. And because we've got this mapping of short IDs to UUIDs, we can then clean out both hashes. So all this all connects, and it works great. And then in order to calculate churn, because we want it to be fast, we want that type of calculation to be small, we use per month bitmaps. And that's where the short IDs come in. How this works is somebody comes in, we create a short ID for them, and then with that short ID, we map it to a bitmap. Redis has this concept of bitmaps on top of strings. You have a string that you can access individual bits, and you can read or write individual bits, which makes, for certain types of problems, very easy and very concise on memory. And so if you have per month bitmaps, and Redis supports bitwise operations on strings, you can say, here's last month's bitmap, and here's this month's bitmap. Find the bitwise AND of these two strings, and then all of the 1 bits are the people who visited 2 months in a row. And then Redis also has a command that lets you count the 1 bits. So now you can calculate visitor churn nice and fast, right? It's great that that particular calculation is fast, and you've got all this other stuff going on to store the data. And you can recycle all the old IDs based on these old timestamps, and we can discard the UUIDs and we can reset little bits. So it's kind of complicated how this works, which is also why it's embarrassing, because we try to build things that are easy to explain and easy to use, and this is a huge pain in the butt to explain on the mailing list, and yeah, it's not very good. How bad is it? Well, let's look at the drawbacks. The memory is based on the size of the hashes and the size of the Z-set, which comes down to about 400 bytes to unique user if you want to look at actual memory use. So if you're talking a million users, that's 400 megs of data you have to store on your server side. If you're talking 10 million, well, it's 4 gigs. Okay, so maybe it's not that bad, but still, it's disgusting memory use for something that shouldn't take that much memory. But really, the second hash can be thrown away, because rather than mapping from short ID to timestamp in the Z-set, we can instead map from UUID to timestamp and remove an entire hash, and we'll just save memory. But really, both the other hash and the Z-set can be thrown away. We can actually replace all this stuff with just sets and just use set intersections. So we can just store UUIDs, and that gets us down to 120 bytes a user. But it gets even worse. If we use 63-bit UUIDs instead of 128-bit UUIDs, we can actually store these in integer encoded sets, and with a little bit of sharding magic, we get down to 16 bytes per user. So from 400 bytes a user to 16 bytes a user. What's particularly embarrassing about that is that I actually wrote a section of a chapter on sharding and counting unique visitors for my book 3 months before I answered this question on the mailing list. And so I'd already solved the problem, I just didn't apply it right. But we can actually do better than 16 bytes a user. Significantly better, it turns out. Rather than storing that kind of information, let's instead of using UUIDs, which are generally randomly generated, let's instead store a per month ID in a signed cookie. And we want signed cookies so that people don't forge cookies, because that is somewhat important. Also, if you want to use these same signed cookies for your login cookies, then you don't want people to be able to forge them arbitrarily either. And basically the idea is you say the lower 32 bits, this ID is this. Well, it turns out that memory use is based on unique monthly counts from last month. And it comes out to about 1 bit per user. And I say about 1 bit per user because typically web requests where you might count these things could come in concurrently. And so you may generate multiple IDs on a single request. And so maybe your unique ID count goes up a little bit faster than your actual number of your ID space for this month goes up a little bit faster than the actual number of unique users. But that's not bad. But it's a little bit worse on the Redis side of things that if you get hundreds of millions of unique users, you could actually get to the point where Redis is having to realloc the string that it stores. And that can be nasty for cache and performance and a few other things, so you'll have to shard your string. That's not so bad. 1 bit per user and you've got a shard. It's not too bad. And you can actually shard inside as opposed to sharding across multiple Redis instances. Anybody have any questions about this particular one? It's kind of weird, but it turns out it works. We can do better. I call this one the very low memory method. When I originally wrote this, I called it the zero memory method, but that's kind of a lie. It's not zero, it's more than zero, but not much more. We're going to again store a per month ID in a signed cookie, just like before. But the operations are, if it's for this month, we're going to do nothing, similar to before. That's from last month. We'll generate a new cookie and increment the unique and return counts as we did before. We're just not going to set any bits. Okay? And if it's an old or new, old cookie or no cookie, we'll go ahead and generate and then increment the unique count again. And that's it. That's our entire operation. Okay? Now this is sufficient to give you unique counts. Now it's not great at counting, at dealing with not duplicating cookies and dealing with cookie manipulation, especially if you've got a cookie from last month. But we can do that a little bit. We can solve that particular problem by just keeping a small hash of recently replaced cookies. So if you keep 5-10 minutes of, hey, these old cookies have been replaced by these new cookies, and if you have a way of hashing browser identifiers so you can identify a particular client, say by hashing their plugins that they pass, and perhaps by hashing their user agent string, maybe even a few other pieces, you can use that to map from your no cookie to your new monthly cookie, so you can minimize duplicate unique changes. The magic about this is you have no per user overhead. You just have how many users have visited in the last 5 or 10 minutes, and that's your memory overhead. And so you can support billions of unique users every single month and use a few thousand bytes of memory. And so now you can actually run this on a tiny, tiny machine anywhere. And the only issue you run into is, well, maybe that machine is not fast enough to deal with the number of queries that are being performed. And so these are the kinds of operations and optimizations that are pretty common with Redis. You start out with an idea that solves the problem, and then you incrementally improve it. And we went from 400 bytes a user, down to 120 bytes a user, down to 16 bytes a user, down to 1 bit per user, down to a few thousand bytes for as many users as you ever need to support, which is not bad. Okay, so now we're going to get to the tangent on Zsense. This is just a filler slide so I can go into tangent. In Redis, Z-sets are these amazing things. Okay, they're most commonly used for top lists or for even timed queues. So you can put a timestamp in there and an ID that you can use to reference some other thing to process. And they're great. Okay, they're fast. They're login performance to insert, update, or delete. You can scan, and it's nice and fast, and it works great. The problem is that typical storage is on the order of about 115 bytes per entry for modest size Z-sets of up to about 1,000 entries. But once you start hitting, say, 100 million entries, it goes up. At Adley, a former company that I worked for, we used a variety of Z-sets to store this kind of information. We actually had a queue of Twitter users. Of all the Twitter users we knew about, we had a Twitter ID, and then we had a timestamp for when we should scan them, or when we should fetch information about them. Now this is great, except for one problem, and that is those 155 million Twitter users took up about 40 gigs of RAM. If we ever needed to cycle the machine that data was on, it took 20 minutes to load that data into memory. If we ever needed to save it, it only take a few minutes to save it, but then that was a few minutes that nothing else could go on. And really 40 gigs of memory to keep a queue of 150 million items is a little much. One of the tricks we use to solve this is realizing, wait a second, we've got these bitmaps, and we've got these integer IDs that are all sequential. The max integer ID that we were working with at the time was about 350 million, which seems like a lot, but it isn't really. If we just stored a timestamp in it, say a bitmap, a sharded bitmap, and we kept a queue that were ready as a separate list, because you can pop items off of the list in Redis, then we could, not unreasonably, just have a process that scans this bitmap looking for things that could process, puts it in this other queue, and anytime that queue got big enough, we stopped processing. And anytime we needed to refill this other queue, we continued processing through the bitmap. And we ended up just using 2 bytes for each one. And those were, what day should we go ahead and fetch this region? And that cut us down from 40 gigabytes to about 700 megabytes. It's a huge savings. And we used a couple other tricks to take a couple 4 gigabyte and 10 gigabyte hashes down to similar sized data. And so overall, at the time, when I pushed out these changes, we went from storing about 60 to 70 gigabytes of data in Redis down to storing about 5 to 6 gigs of data in Redis. It was a huge cost savings, factor of 10 in terms of data stored. And we saw no appreciable difference in performance. Everything else just worked. And so if you're thinking about using things, you have big queues, or if you can lazily pull things or scan through large data structures, you can actually avoid some of the memory costs associated with Zsense. And if you've got hashes and the keys are based off of integer IDs, and you've got fixed size data, you can also store those in bitmaps. You can get huge cost savings. Okay, done with the tangent. Anybody have any questions about that optimization? Okay.
I have a general question.
Okay.
Typically when you have some sort of data store, whether it's hash or whatever, if I take it's ordered, or so you can do a binary search so it quickly recovers. I'm trying to find out what's underneath. Is it a big B tree underneath, or
For which structure?
For Redis?
Well, so the key space in Redis is a hash table. So the keys, like all of your keys, is just a hash table that maps to some structure. And then the structure is varied. So a string is literally a string. The list is a linked list. The set is a hash without values. The hash is a hash table. Actually, the same implementation as the one in the higher level key space. And the Z set is actually 2 structures. It's a hash table combined with a skip list. And so that's how you get the indexing. Sorted indexing is the skip list side of things, and the member lookup is the hash side of things.
The performance is different depending on the data structure, and it's
Exactly.
all documented
Yeah.
in the Redis.io
Yeah.
documentation for each call.
Is there documentation somewhere that does get into different ways of using the stuff that tells you how much memory is being used, or like there's like benchmark tools for how fast things are, but are there memory benchmark tools that?
There are not memory benchmarks. Okay. That said, you can write about 10 lines of almost any reasonable programming language. You can inject some data, you can compute size before and after the injection, and it's pretty consistent. That's how I came to be roughly 115 bytes on the Z set side of things. And on the hash side of things, it's about 80, 85 bytes per entry.
Right. But in your case, you were initially using Z sets, but you weren't really using the power of the Z sets with the inner stores and.
Sure.
Oh, you were?
No.
Oh, okay.
We weren't.
You were just okay.
We were using.
But if you want to use the Z inner stores and stuff like that, like that's powerful.
Oh, certainly, absolutely. The thing is, pick an arbitrary data structure that you know about. Are you using all the operations on that at any point?
Right.
Probably not. Usually you end up picking a data structure that offers you the functionality that you need at the moment, and you don't necessarily use it all. And sometimes using that structure is a waste.
Yeah.
In this case, Z sets were a total waste of what we were doing. That's why we ended up migrating from it, because there was this valuable insight that we gained. But for a while it worked. It worked pretty well. And we would have continued using it if it weren't for the fact that, hey, rules kept getting bigger.
Right.
And it wasn't sustainable long term. And if anything crashed and we had to restore, well, that's 20, 30 minutes of downtime that we really don't need.
And how painful was the conversion from a Z set to a hash or whatever, like when,
Well, for us, it wasn't too bad. I wrote a function that ran on our task server. Or no, did I? I can't remember if it ran on our task processor or if I just wrote a script. But it was basically, hey, you got the Z set. It's stored it. Well, let's pull off 1,000 entries. Let's write 1,000 entries to Redis. Let's pull another 1,000. Let's write another 1,000. Pull another 1,000. Write another 1,000. And I think that particular migration took, a few minutes. It wasn't bad at all. And of all the things that I've had to do in Redis, that was one of the least complicated, that migration. Of course, writing the sharded bitmap stuff, that was annoying to get right, especially because I wanted to add, most Redis clients incidentally have what is called pipelining support. And so rather than send like every command that you call makes a single round trip, you can batch up commands for a single network round trip, and that can result in performance increases that are significant depending on your network latency. Typical, if you're running on a local host, you can do anywhere from 25,000, roughly 25,000 round trips a second in Redis. But if you pipeline for simple operations, you can typically do 50, 60, 70,000. And that's on local host. If you're talking about across a network or across, if you're on Amazon, goodness, 1, 2, 3 milliseconds, you can go from a few thousand operations a second to 50, 60,000. And so by batching it up, we get much better performance. Also by fetching larger chunks of data, then you pack more data in an Ethernet frame and less fragmentation, and the network gets better utilization, all that other fun stuff that most people just don't think about when they're building things, but then become a practical matter when you want to scale to hundreds of millions of things. Okay. So, visitor action sequences. So the idea is that we really want to calculate how our funnels are performing. That is, if somebody clicks on something, it goes through some process, and there's some destination you want to have them at, whether that's posting a comment, uploading a picture, making a purchase, anything like that. We want to see how those funnels are performing. The problem is most of the funnel analysis software look like this, and they blow. Or suck, depending on your perspective. The colors are kind of hard to see. But this is actual analytics, Google Analytics from ChowNow's online ordering. The interesting part is that there are basically two entry points. The blue in the first part and kind of fuchsia, okay? But they switch positions because people will alternate back and forth. And there's an optimized flow, but not many people do the optimized flow. A lot of people have to click through a few different places, and some people have to log in. Some people have to sign up. And so by the time you get to your conversion, your last step, you've lost a lot of those things because of the way this is structured. You can't just say, just show me all traffic that goes through this one little path. That's not possible. And so either you pick some third-party provider that actually provides those kinds of statistics, or you sit there with a spreadsheet and you start typing information in and keep adding numbers until you get your right, until you calculate the proper funnels, and you calculate your drop-off rates for logging in, and people who are already logged in, and things like that. And that gets to be in the fly. So, you may as well just do it yourself, especially because it's not very difficult once you have Redis. And so this first method, which is the sequence method, is probably pretty obvious. And that is, each user gets a list. The nice thing about a list is, well, I'll get to that in a second, and when somebody performs an action or visits a page or what have you, you add the user to a Z-set, this member being the user ID, and the score is the time. And then every time somebody visits, you are push the action on the end of the list. And that is, push the item to the right, and over time you will have the actual action sequence, and it will be right there, and that's convenient structure. And then you can clean up and analyze all of your old sequences by looking at your timestamps. And this is also one of those things where you can optimize it using that method that I described before. Although presumably, you're probably going to want to check action sequences after an hour or 2 hours or whatever. And so maybe this ZSet won't get very big, and maybe those number of lists won't get very big either. Of course, there's some drawbacks. And that is memory use can be extraordinarily high for very active users. If you imagine the visitor action sequences of a site like Facebook, if you can imagine analyzing sequences on Facebook, and how many actions do a typical user on Facebook do? When you log in, you're like, oh, I got 20, 30 minutes, I'm going to do this. You're reading, you're liking, you're commenting. You can do 400, 500, 600 actions in 20 minutes. And that wouldn't be unexpected. And also, depending on the detail level of your events, each individual event can be expensive on the memory side of things. And so the more users you have, the more memory you have, the more each individual user does, the more memory you have. We talked about memory use of unique users and our churn analytics. Well, now maybe you don't have quite the wide range of time, and so maybe fewer users, but each of those fewer users may be using a kilobyte, 5 kilobytes, 10 kilobytes, depending on their action sequence. We can improve that, maybe quite a bit better. And we use bitmaps. And the basic idea with bitmaps, again, is you limit your unique events, and you map any individual event to an index in a bitmap. And each user gets a bitmap. All you do is you again set the entry in the Zset, and you write that bit to the bitmap depending on the action, and you can clean up and analyze the exact same way you did before. Now, one of the benefits of this particular method is that when you're in a situation where you need to analyze, of the people who were logged in when they first visited, how many people visited this page before completing my conversion, however you want to call it conversion. And this particular operation is really fast. It's just a bitwise operation on a string. Wonderful. Now you do lose, this action happened before this action, but it's not always necessary depending on the particular flow and depending on your memory use, your memory limitations, we'll say. But still, this can do all sorts of very, very nice things on the analytics side of things. So yeah, I'm a big fan of this method because, well, you don't get crap graphs like I showed you before. You can actually show your funnel, and you can actually inject intermediate sequences when you're showing your process and your flow. If you've got tend to be a linear flow, and if you don't have a linear flow, you tend to have a tree-based flow. Of course, this one has drawbacks. Again, more strict sequence analysis, and in this case, memory use tends to be dominated by Zset storage, basically because each Zset entry is 115 bytes, roughly at minimum, and so that's the equivalent of some 1,000 actions that somebody needs, unique actions that you can have available before that bitmap starts taking over. Any questions? So, geo-notifications. This is kind of the odd man out, but I like this particular problem because it can solve a certain group of problems that a lot of these location-sensitive platforms have nowadays. And basically, the problem can be defined as there's some events that are occurring, and you want to send these events to nearby users that are nearby this particular event. But we don't want users to be notified too often. The last thing you want is for a user who's walking by a store or a sports event to be notified 1,000 times as they're walking by the sports event. Hey, I love this game, whatever. You don't need that. You don't want that. And so you need to be able to reduce the number of notifications and the notification radius as the number of notifications rise, and similarly increase the radius as the number of notifications fall. And this would also be useful for something like Uber. You know, if you've got a cab driver who's sitting there, you know, he doesn't necessarily care about every person in a city. He only cares about those ones that are nearby him that he can get to and pick up really quick. Okay. But also, we want to be able to support the ability to fetch history. So, you know, when I connect, I want to see the events right around me immediately, and then I want to get more or less real-time updates. So, the basic solution to this problem is to consider the world as a recursively divided set of blocks. So say you start out with a 1 degree by 1 degree block, and then inside that you've got 4 half degree by half degree. And inside those 4 half degree by half degree, you've also got 4 quarter by quarter. And inside those, 4 8 by 8, et cetera, et cetera, et cetera. And basically, if you have a person at a particular point, you go ahead and have them subscribe to all blocks and all levels, from the coarsest all the way down to the finest that they might be interested in. And at any time you have an event that's written to a point in the real space that you're mapping to, you first add the event ID to a Z-set in as deep of a partition as you would ever expect. When I was answering this particular question, I said 12 levels deep. 12 levels deep, it turns out that if you're dividing by half, gets you about 30 meters of resolution, which isn't bad. You write to your Z-sets, write to 12 Z-sets on your way down, and then you also trim your Z-sets as you're going along to trim how much time. Say that you only ever want to see 10 events every 15 minutes. Well, as you're adding them, you can always toss out anything that's more than 15 minutes old on your way down. But then you can also check the size of the Z-set after you've trimmed them, and that becomes important in a second. Oh, and we can't see that last one. Okay, so the next one down is after you've checked the size of your Z-sets, you know how many events have occurred in the last 15 minutes. And so you find the highest level Z-set that has less than your cutoff. So if your cutoff is 5 for 15 minutes, so the top level one is 1,000 events. And the next level down is, say, 150 events. And the next one is 30 events. And the next one is 20 events. And the next one is 4 events. And once you get to that 4 events, now you know the particular channel to publish to because you've reached the number of events. You found the radius that is within your limit, and you can publish that entry. And now everybody who cared about that particular region can get a notification. And this just naturally scales for, you know, a huge number of notifications, and also scales to a tiny number of notifications. If you've got a tiny number of notifications, then everybody on the top level will get a notification. Whereas if you have a huge number, mostly people at the bottom. And this naturally scales automatically. Of course, there's a couple drawbacks, because all of these problems have drawbacks. Nothing is magically perfect, except for me. Kidding, of course. I always saw a smile. Now you go laugh. Tough crowd. Drink more beer.
There we go. That's a good recursive algorithm.
Huh?
It's a good recursive algorithm.
Yes. It's a great recursive algorithm, and it can even be done iteratively as well, procedurally. The biggest problem with it is that the ID and timestamp notification is duplicated. It can be duplicated up to 12 times. So every event, you're talking 12 by 115. So you're talking about a kilobyte of data just to store the history. And large histories could use significant memory, but you can actually improve this by just storing the events in the list. Because it turns out that if you store the event IDs with a timestamp, anytime you write to it, you can also just go and say, well, hey, while the oldest entry is too old for me to care about, go ahead and pop it off. And you can actually write a Lua script to do these things And so it'll be one round trip to Redis. You don't need to do all these things. It can even return the actual level that you want to execute on. And this particular Lua script to do this is fairly concise, although you should calculate your cells in advance.
Wouldn't you hash the events so that when you write 12 copies of it, you just write 12 hashes?
What do you mean by 12 hashes?
That you have to do 2 lookups. You find an event to notify, and then you go to the hash set and find out what is the notification that's sent.
Well, sure.
So
That's the history side of things.
Yeah.
But when you publish to subscribers, rather than sending an event ID, you actually send the whole event that you want to notify. You send all the data. And so that way, all of your listeners get all the data that they need. They don't then need to make a request to pull that data. And of course, any old data, if you've got a Zsense with a huge amount of data and nobody's updating it, then it just kind of hangs around memory forever. But we can add a little bit of expiration to that, call it 15 minutes if you only care about 15-minute blocks, and then they naturally disappear over time. And everybody wins. Old data is discarded automatically. As you're writing data on active things, data gets discarded. It's good. Okay, yeah. So, and that's about it about this particular group of problems. Do we have any questions?
So presumably for the geo, are you using geohashing for the lat long?
It's not necessary.
Okay.
In this particular case, it wasn't part of the problem. The 1 degree by 1 degree grid cursively divided was actually part of the problem statement that somebody requested.
Okay, because my question is going to be how do you address the precision the boundary problem? If I'm searching within a array,
Redis, yeah. So one of the things that you can do if you have an issue where say you're on the edge of a block, you care about things that are close, but if you're on the edge, well, thing just on the other side of the block is also very close. So what do? And the simple answer to that is you subscribe to multiple blocks at any particular level. And then you get all of the natural nice things where the subscribe goes out. And it turns out that Redis will keep a little bit of memory for each unique subscription, and then a little bit of data to reference the particular connections that are waiting on them. And so the amount of memory is relatively small. And you can calculate it more or less based on how many cells are you listening to. Are you listening to 100 cells? Are you listening to 1,000 cells? I hope that when people are actually if people actually use this in production and not subscribing to 1,000 cells, they're maybe 50, 75, something like that. And this will reasonably scale to a large number of users. When you connect to it, Redis forks, dumps everything to disk, and then sends that dump off to the slave, and then sends any delta between when the fork happened and right now off the slave, and that's how it starts out. In Redis 2.8, it will have an incremental method so that if you enslaved before and there had been a network interruption, when it reconnects, it will just send the delta up to some memory limit that you can specify in the configuration. So it can have a fast recovery of reslaving. And that's a feature that has been wanted for years. Will be coming out soon. Any questions?
About adding new shards to your cluster?
Adding new shards is kind of a pain in the butt. Generally, you should probably be doing power 2 sharding, where you should be pre-sharding, and then you can run multiple Redis servers on a single physical machine on different ports. And the Redis overhead is relatively low. And because Redis is single core anyway, if you've got 8 cores, you may as well run 8 Redis servers on it. That way you can at least scale to 8. There's some tricks about assigning Redis to different cores in order to optimize network I/O and an actual throughput. But on a remotely accessible perspective, there have been people running 16-core machines that get 100 or 1 million operations per second out of that machine. Although on a local host over a Unix domain socket, I've gotten about 1 million operations a second. And that's on Core 2 Duo 2.4 gigahertz. It's my desktop machine at work. So you can get some extraordinary performance out of it. Yeah, you should pre-shard and then do power of 2 splitting. You can also do crazy things like using different databases. Redis has this idea of numeric databases. And so you can put your data in different databases. You pre-shard on the database. And so if you have 4 instances on a single machine, you have 16 databases, then you can have 64 shards. And then if you want to reshard, then you can either you can slave, you can cut over your clients, you can delete data that you don't need. That works pretty well. The only thing kind of funky about databases is that when you've got multiple databases, that expiration thing, those 100 probes are performed on each database. And so as your number of databases increases, or the number of databases that you use increases, the amount of time it spends doing that random probe increases. There's some people who run, I think, up to 255, 256 databases. I tend to stick with the default of 16, because I usually can. And I personally usually partition based on the type of data being stored. So cookies are stored in database 0. Some general caches are stored in database 1. And search indexes are stored in database 2, things like that.
Do you always do that by default? Use multiple databases?
You get more write operations
Say
that way? You get more write operations?
You don't get any more write operations on a per database basis. It's still single core for all the databases in a single Redis server. I do that just to partition my key space. So if something bad happens and I need to clean things up, at least I don't have my search index, which tends to have many millions of keys. I don't have to worry about that. On my cookie side of things, if I want to clean out some cookies because I messed up one thing or another, I can just scan through my cookies, do what I need to do, and then do that. That's just an overhead. Also, if you decide you want to, generally speaking, it's a good idea to run a different Redis instance, like a different Redis server process for each different kind of data. Because if you start out with it all on one machine, then if you want to move it to other machines, it's pretty easy. You shut it down, ship over your dump, start up a new machine, and it's all a configuration thing. With databases, it's similarly easy. You just slave, cut over, delete the databases that aren't necessary on a different machine. It's a similar kind of thing. You're only loading more data on the slave or on the new machine. But if it's all sharing a key space, then you have to do key space cleanups anytime you want to, say, oh, well, this particular part of my application is growing. Then you have to do nasty things. Like pre-partitioning based on database or based on Redis server, then that is a migration that becomes 1,000 times easier.
With the pub sub channels, how far does it hold any look back? Or
No,
is it just
there's no look back. If you're not connected when the message goes out, you don't get the message. That's why we had the history for the geo notification stored in the Zsense. Yeah, it's a bit of a drawback. If you're interested in doing those kinds of things with look back, that actually becomes a one-to-many subscriber model. You can think of that kind of as a variant of the Twitter broadcast style. And if you read chapter 8 of my book, you'll learn how to build Twitter in Redis. All of Twitter in Redis, including the streaming API.
the scalable Twitter?
I talk about that in chapter 10 and 11. And specifically how to scale all the different bits, using spread scripting and sharding and a few other things. I wouldn't do it, and it would cost a lot of money to scale to Twitter's size, but it's not impossible. But again, I wouldn't do it. There's so many better ways of doing it.
if you're running just say 1 million gets off of a local host, back end, and you were to then start combining it to like a multi and an exec, like the 2 per, running 500,000, and then 4 per running 250,000, etc. How much speed up are you getting feeding into your local host anyway?
The multi-exec doesn't improve performance. Multi-exec is strictly atomicity.
Okay.
Where you get performance is just by batching up your sequence. And the clients, the Python client, I very much like, because you can say, I want to create a pipeline with a transaction, or I want to create a pipeline without a transaction. And without a transaction is genuinely as fast. And actually, they're both very relatively fast related. They're very close, within a couple percent. That's because they're implemented the exact same way. Batch up all the requests, create the protocol that you're going to send it across the while on one node. And when you get the response, parse the response as it comes in, batch it up, and then return that to your caller. And so really it's about whether your client supports batching up requests or whether it sends it and waits for a response. And some of the clients don't offer pipelining, that type of batching up the requests without a transaction, which is a little unfortunate. But that's client dependent. And yeah, on a related note, if you're using Node, there are no transactions. Sorry, you get screwed. And that's just because the library that supports it on the Node side of things never thought that type of thing was important. But you can get about 95% of Redis's transactional support using Lua scripting, which is really the only viable option on Lua if you want to do those kinds of things. Like get, fetch, manipulate data before writing it back.
I noticed that when you were talking about kind of splitting up the types of data that you put, like the cookies and stuff like that, are there, and then when you presented the problems, so like you kind of went from looking at the high memory distributions and low memory distributions. Are there kind of like other things that, if someone's new, that you'd say, okay, these are some kind of best practices that I probably have to go from looking at things from a high memory to a low memory kind of way?
There are a lot of things. There are 2 resources that are really good at this. First resource, which is free, is at redis.io. There's a section in the documentation that talks about memory optimization, and that's pretty good. And it talks about a lot of the different things. The second resource that I know of that tries to be complete is my book. It's about optimizing memory using Redis-specific things. That is chapter 9. Yeah, I think it's chapter 9.
Copy of the book here?
No. Okay, so I signed off on the manuscript yesterday, and I signed off on the index today, which means that it will be printed soon.
Does it have a title or a publisher?
Yes, it's Redis in Action. It's at Manning. It's through Manning. So if you're familiar with the In Action series, this is another In Action book.
Yeah, it's chapter 9.
Huh?
Chapter 9, it seems.
Yeah. You can buy it electronically now. The electronic version that is available right now has a few errors that we knew about before it went out, but we didn't get them in time. We didn't get the fixes in time. In fact, I sent a few fixes yesterday. But it is very good, almost the exact same you get if you buy the book. And most of the errors are small, like minor text things, or this figure should be indented differently, or minor things like that.
How long before the electronic version is fixed and at parity?
The standard PDF that's available will be available in the corrected form within a day or two when the dead tree version is available. Kindle and Mobi format will be available approximately 2 weeks after the book is released. You can't buy it through the Kindle store because they like to sell books at $10 a piece. But if you buy it at Manning, you'll get the Kindle and Mobi version. If you end up buying the book through some other retailer, you can register on Manning and get the electronic copies for free.
And even if you buy it now, you'll get the fixed version when it's ready.
Of course, yeah. And if you buy the electronic version, only the electronic version, you'll get the updates. And even if you pre-order the Dead Tree, you'll get the electronic version updated. And if, yeah, there's the early, you can go and you can buy it there. You can buy it now. There is a deal for 39% off. If you look at the right places, it's always available. If you look really, really, really hard and follow me on Twitter, I will post when there's 50% off deals. Or if you're a previous purchaser of Manning books, they usually send out, hey, these are deal of the week or deal of the day kind of things. And if you troll that, you can get a good deal on it. Or you can...
Maybe we can put it like on the meetup page if that works for you guys.
The link? Or
If you want to do like a discount to the group.
Yeah, I can see if I can get a discount to the group. Usually those discounts last about 24 hours, 48 hours, so it's relatively short-lived. 39%, which is a pretty good deal, is you can look for it and find it. Well, I'm not going to tell you how to look for it and find it, because that actually costs me money.
Great. Thank you.